Welcome to the course on power quality. So, we will like to cover this active series power filter. The outline of the today lecture will be like introduction on series active power filter. We will talk about your state of art on series active power filter, then classification of series active power filter, then the principle of operation of series active power filter, and analysis and design of series active power filter, control of a series active power filter, modeling simulation and performance of series active power filter, numerical examples, summary with references. So, this is the outline of the typically lecture. Coming to objective, we will like to discuss the requirement and applications of series active power filter, then we will discuss configuration of active series power filter, then control of active series power filter, analysis and design of active series power filter, then the method of modeling and control of active power series filter. Well, coming to just to introduce the series active power filter. The voltage based power quality problems in distribution system are like a voltage quality problems with the like a voltage sag, voltage swell, voltage unbalance, voltage flicker, voltage tangent, voltage notches, voltage fluctuations, then voltage waveform distortion, voltage imbalance and voltage harmonics. So, to mitigate that normally we use the series active filter. So, these power quality problems increase losses in many loads and sometimes trip the sensitive load causing the loss of production, and solution is the series active power filters for these problems, and series active power filter protects such sensitive load from these distortion or disturbances in the voltage of AC mains, and the multi dialog active series filter uses high frequency isolated gate polar insulated gate polar transistor technology with the digital signal processor control, and these are the typical photograph of these filters. And coming to state of art, the series active filter now is the mature technology to eliminate the voltage harmonics, to eliminate voltage spike, to eliminate voltage sag, to eliminate voltage swell, to eliminate voltage notches, to eliminate the voltage terminal, to regulate the terminal voltage and to suppress the voltage flicker, and to mitigate the voltage unbalance in 3-phase system. Like now, the development, these series active filters are developed in varied configuration with the advanced control technique and different solid state devices and improved sensor technology with typically require Hall effect current and voltage sensors, and of course, it is used with cause of microelectronics revolution, the microcontroller and DSPs to implement the control algorithm online, and these are typically the how you look into the Hall effect current sensor and the DSP board which used for implementing the control algorithm. Now, coming to classification of this active series filter power filter. First classification is on converter type, whether we use the current source converter bridge structure or we use voltage source bridge structure, and topology wise whether we use half bridge or full bridge, or for based on number of phases like 2-phase single phase, 2-wire single phase, 3-wire 3-phase system or 4-wire 3-phase system. And of course, coming to the first type of converter classification. So, this series current source converter based series active power filter, you can see that in series with the injection transformer, we are typically injecting the voltage harmonics or the typically the voltage magnitude with this current source inverter, and current source inverter you have a DC link capacitor as a energy storage element. This certainly have a problem of size, cost, weight and losses also, and the device here switching device is also, because current source converter needs a negative reverse voltage blocking capability which your IGBT do not have. So, we have to use the series diode. So, this is you can call it typically the total bridge consisting of, and you need the mandatory this capacitor also. This current typically this your voltage will be PWM kind of current generating the voltage. So, you need this capacitor like also. So, it will be providing virtually the voltage compensation in series. But of course, it is also interestingly series active filter also used for in case of voltage fed kind of load to mitigate the current harmonics also. We will discuss that. Voltage fed kind of load, the series active filter is the best for compensation for current harmonics also. So, these current source converter are considered sufficiently reliable, but have high losses and require high value of parallel AC power capacitors, and they cannot be used in multi-level or multi-step modes to improve the performance in high rating. This is the like a voltage source based single phase active series filter. I mean, you have a now voltage source inverter here. In voltage source inverter, you have a IGBT with anti-parallel diode, and well, losses are low because either IGBT will conduct or diode will conduct. I mean, compared to the current source, the loss will be less in the switching devices as well as conduction also. And then on DC link, we have electrolytic capacitor as energy storage element. This also have a small size, low cost and small losses. And then I mean, you do not need any element on the AC side, but of course, there also you need the injection transformer. So, here also we have a injection transformer. Maybe in single phase we do not need some time for small rating injection transformer also for injecting this voltage like but this I mean compared to the shunt filter, it has a more application, not only voltage based compensation, but in voltage fed kind of load it also eliminates the current. You can call it current harmonics also, will come with the example. So, it is considered more versatile, like you can think about. So, these voltage source based series active filter are lighter, cheaper and expandable to multi-level and multi-step version to enhance the performance with the lower switching frequency. And coming to the classification on topology based classification. So, you can use this voltage source converter also with the half bridge, I mean here, and it can also inject the voltage by generating, but the only drawback is that these capacitors required quite high value because the whole current will flow through these capacitors. Then this is the bridge structure which is preferred, I mean for shunt series active filter. I mean, and the major benefit of this is like in single phase it can operate unipolar. So, the voltage ripple here which are generated is corresponding to double the switching frequency, or you can say for same PWM waveform you can have a half the switching frequency, which reduces switching losses in this single phase voltage source converter working as a series active filter, and it capable of injecting certainly a suitable voltage which can compensate the voltage, I mean which are have a voltage power quality power supply, or it can block also harmonics by injecting the appropriate voltage with proper control. So, coming to the supply based supply system based classification. I mean, this is like a single phase 2 wire X series active filter with the bridge structure that we are injecting in the single phase with the kind of voltage injection here. I mean, and this is your 3 phase 3 wire. I mean, like self supporting bus, we are injecting the 3 phase voltage. I mean, in this case, and you can have either linear load nonlinear. So, it can be improving typically your in voltage fed load current harmonics, in current fed load is compensating typically the voltage also. I mean, like so capable of virtually versatile more applications like, and then this is you can call it 3 phase 4 wire. So, you have a even 3 independent leg here and you are connecting in series with that like, I mean, so automatically you can call it, even if you are compensating neutral your harmonics current, so neutral current automatically will be mitigated. I mean, maybe you have a 3 phase 4 wire kind of such kind of load, or otherwise like, I mean you are compensating the voltage based compensation. So, this is for 3 phase 4 wire like. Coming to principle of operation of this series active power filter, I mean this is with the taking a case of 3 phase voltage source inverter connected in series with the 3 phase supply through 3 single phase coupling transformer. I mean it is here, and of course, this is 3 phase VSI which is working typically your series active power filter, I mean compensating typically the voltage power quality problems across the load, or regulating the voltage even across the load. So, those all things it can do voltage regulation also, and it can be very specific solution for a specific kind of load. And this is the point which I was mentioning, like for the voltage fed nonlinear load which consists of capacitive filter and equivalent load at the DC link of the 3 phase diode rectifier, a series active filter can also effectively maintain the sinusoidal supply current. And whereas the current fed kind of nonlinear load which consists of series connection of a resistor and inductor at the DC link of 3 phase diode bridge rectifier or thyristor bridge converter, a combined system of shunt passive filter and series active filter is to be employed to effectively maintain the supply current. So, that load is not really affected by that, but a series filter will be forcing the entire harmonics current into the shunt passive filter. So, series filters are typically used for a small rating in those applications also. The control algorithm series active filter is to eliminate current harmonics and is suitable for both series active power filter and hybrid configuration of series active filter and with shunt passive filter. For voltage sensitive load, to eliminate the voltage harmonics, unbalance, and to maintain zero voltage regulation of PC, a series active filter is directly controlled to inject sufficient voltage in series with the supply. And this is the typical case you can think about, which I was mentioning, that you have a here voltage fed kind of load, typically, and you draw very you can call it uncontrolled current, and the equivalent of this you can think about how it is really behave typically, and you can inject the typically a voltage in a way that you can reduce the harmonic current also in that. So, that is typically a voltage fed kind of load, means a diode rectifier with capacitive filter and then equivalent load here, that is we call it voltage fed load, and can be represented equivalent to like a kind of voltage which is getting reflected here, but current certainly will be kind of uncontrolled in that case. So, you can inject another voltage here, so that this current is sinusoidal like also. So, the load is represented as a voltage source with a fundamental as well as a harmonic voltage, and the harmonic current originates from this rectifier voltage, and the series active power filter is controlled as a current control harmonic voltage source to offer low impedance at the fundamental frequency and acts as a high value resistor for harmonic currents in the AC mains, and this satisfies the need of harmonic currents required by the load and prevents the flow of harmonic currents into the AC source. And along with this, a series active power filter requires a small fundamental voltage drop across the coupling transformer to draw active power for maintaining the DC bus of voltage source converter, which normally realized with the help of control like. So, this is a typical example of if you have a, you have not given circuit of it, no? You could have given circuit anyhow. We have a this waveform corresponding to 3-phase diode rectifier, and if you put a series active filter, you have a supply voltage, you have a load voltage, and you can force the supply current to become sinusoidal in phase with the voltage, and capacitor will be charged corresponding, and this is the you can call it the injected voltage. So, but if you inject this voltage, you will have this kind of load voltage like also. So, coming to analysis and design of series active power filter, this is typical, you can call it the case we were talking about from the design point of view, that you have a load here and you have a 3-phase series active power filter along with that. So, coming to the design parameter of T-STATCOM, this is 3-phase 415 volt, supply voltage per phase is 239.6 volt, and a load is 25 kV kilowatt load, non-linear load with a 3-phase rectifier with capacitive filter, and switching frequency is 10 kilohertz. Inductor current ripple is 5%, and DC link voltage is 700 volt, and your DC link voltage ripple is let us say 5%. So, now coming to this design of voltage source converter for series active power filter. So, design of this series active power filter is based on the DC bus voltage of the 3-phase rectifier load, and the series active power filter is operated for eliminating the harmonics in the supply current, and hence the inject only harmonic voltage. So, it is clear that the fundamental component of load voltage is the PCC voltage, as the series active power filter inject the harmonics component of the load voltage. Hence, the fundamental component of load AC voltage is typically your VLL under root 6 upon pi Vd, and that is your 0.779 Vd, and for a given line voltage of 415 and a DC link voltage of 540 volt, and the voltage rating of the series active filter is obtained from the difference between PCC voltage and load voltage. Hence, the series active filter is calculated as typically from this relation, so 2 upon 2 pi, and this is virtually we do from starting from your 0 to pi by 3, that is first 60 degree. We have a sine wave minus, because we are forcing now by series active filter to conduct all the 3 phases. So, during conduction first 60 degree you will have a supply voltage minus the voltage reflected from the DC link, okay, that is this, and second segment is where the voltage sine voltage will be this, but it will be 2 Vd by 3 reflected voltage on that, and the third will be like typically your 2 pi by 3 to pi up to 180 degree, and this is Vd by 3. So, that is you will find the waveform and then d theta, and when you take this RMS of this square root of this, it comes 75.6415 volt, and you have a typically the supply voltage 239.6 and the DC link is 540 volt. So, from that we have calculated this value of filter voltage across the series filter, and the current rating of the series active filter depends on the fundamental component of load current, and it is obtained as the load power is calculate as VD square by R, that is PD, and where the R is equivalent resistance of the DC load at the output of diode bridge rectifier, and for a given load of 25 kV at 540 volt, the DC bus voltage and equivalent resistance is your from this you can calculate 11.664 ohm. And considering the unity power factor, supply current and lossless series active filter, the RMS current is calculated from ISA equal to P upon P divided by root 3 VLL, that is 25,000, or you can call it 25 kV kilowatt divided by root 3 415. So, current supply current is like 34.78 ampere, and the current rating, because it is connected in series, so current rating of your voltage source converter of series active filter will be also your IF equal to 34.78 ampere, and the kV rating of VS, you can call it series active power filter, will be that is will be equal to kV into 3 VF IF into divided by 1000. So, this is 3 phase. This is the voltage of series active power filter, which we calculate 75.6415 into current flowing into 34.78. So, the rating comes 7.892 kVA. So, the injection transformer is designed considering the optimum voltage level of the voltage source converter, and maximum AC voltage on the AC side of series active filter may be that MA VDC by 2 root 2. So, from this putting the value here, when we get the 197.99, it will generate, and at the modulation index of 0.8, and it is on the supply side, it must be VF equal to VF, and the turns ratio from the coupling transformer is your typically the turns ratio NVSC upon N supply. So, from this you can find out the turns ratio of 2.62 volt. I mean, like from this voltage we are generating this voltage, that is the turns ratio, it has to be there, and the kVA rating of the your injection transformer is same as the kVA rating of the voltage source converter, and it is calculated as kVA equal to 3 VF IF divided by 1000, and the putting the value, I mean the 3 times the voltage of the active filter, current of active filter, it comes 7.892 kVA. Then the DC capacitance of VSC of series active power filter, and that we certainly calculate from the same energy balance formula. So, DC bus capacitance is selected based on the transient energy required during the change in the load, that is half CDC VDC square minus VDC 1 square equal to 3 VF IF delta T, and where the VDC is the rated voltage, VDC 1 the drop in the DC voltage allowed during the transient, and delta T is the time for which the support is required, and CD is the capacitance, and we considering the delta T equal to 0.1 millisecond. So, keeping the value all value in this case, I mean calculating VDC is normally same as 700 is reference, this is reduction 5% 660, it will become 665, and putting the all value, the capacitance comes like your 3304 microfarad, and hence a DC bus capacitor of 4000 microfarad with 700 volt rating is selected for series active power filter, and the value of interfacing inductor is selected based on the current ripple in the current of the series active filter, and by considering the ripple current in the inductor of is 5% and overloading factor of 1.2, the inductor is calculated as LF equal to N VSI upon S, so and the ripple current, and from this putting all the value here, the inductance comes 10.148 millihenry, and hence the interfacing inductor of 12 millihenry at 40 ampere current carrying capacity is selected for series active power filter. Now, coming to the design of ripple filter, the ripple filter is designed for eliminating the switching frequency ripple from the injected voltage of the series active power filter, and the ripple filter is a combination of capacitor CR and RR connected in series, is generally tuned at half of the switching frequency FR, which is calculated as FR equal to 1 upon 2 pi RRCR and FS by 2, that is 5000. So, keeping the value, I mean typically 1 upon 2 pi RRCR. So, considering RR equal to 5 ohm, it gives the capacitance 6.67, and we can select RR 5 ohm we selected, and we can select from this little higher value that CR equal to 10 microfarad to design the ripple filter. So, that is about the design part of different component with the some guideline. Coming to control of series active power filters, the control here, I mean we will like to discuss only phi control. I mean we discussed already earlier for elimination of voltage harmonies. So, what we do here, of course, we have to regulate the DC link voltage. So, we have a sense DC link, reference DC link voltage and sense DC link voltage, and we use the low pass filter, I mean to get the DC component here, and this we regulate with the help of oscillating controller. Why we use proportional integral control? This is the minimum form which can make the steady state at 0, but this output we consider a voltage drop to take care of the losses in the your series active power filter. Then certainly we sense the voltage, line voltage, we calculate the phase voltage, and this we with the help of we sense the load current, from which we do the PLL, we calculate cos theta sin theta, and from this we calculate the VSD VSQ. So, it will certainly will have your DC component corresponding to fundamental and some ripple also in it. So, we have to use the low pass filter for getting DC component, and this we subtract the loss component from it. So, we get the, you can call it VD to be injected virtually, that is for corresponding to your active power, and similarly we have a quadrature also, and here we regulate the voltage. Typically we have a reference voltage, we have estimated amplitude of the voltage. So, we put again PI control for that also. So, this we call it a voltage which have to be injected for regulating the voltage, plus the voltage corresponding to which are having from line equivalent. So, we add and we get the VQ quadrature component. So, using the DQ reverse part transformation, we are able to get the load voltage for A phase, B phase and C phase, and we sense the load voltage and put the indirect current, indirect voltage control in the voltage source converter used as your series active power filter. So, this is what we call it your SRF theory or DQ theory for series active filter control. And the component typically we coming to the expression of PCC voltage in D axis AG or V AC DC component AC component, similarly quadrature also DC component is, and you have to the harmonics and oscillating component are eliminated by using low pass filter, and in order to maintain the DC bus voltage, a PI controller is used at the DC bus of the voltage source converter, and output is considered as the voltage loss for meeting the its losses, and this is typically the PI controller we are keeping on the DC link voltage typically to take care of equivalent to the voltage loss, for which we have to have some voltage corresponding to the loss, and this is the reference DC link voltage of shunt series active filter, and this is the your filtered DC link voltage of the shunt series active filter, and the amplitude of load terminal voltage is controlled to reference value using another PI controller, and the output of PI controller is considered as the reactive component of voltage for voltage regulation of load terminal, and this is the typically again the PI controller, where it is the input is the error reference voltage at load terminal minus the your amplitude of your load voltage after of course filtering, like the direct axis and quadrature axis voltage component of the reference load voltage we get from the your DC component minus the that PI control output, and similarly for quadrature component, that is the typically coming from load and from PI controller, and the 0 sequence is 0. And now we calculate the reference load voltage VL star A, VL star B, okay, and VL star C in ABC reference frame using this your inverse part transformation, where VD VQ 0 star reference are here, and using this we are able to get VLA, VLB, VLC star, that is the load reference voltage, and we sense the load voltage and then indirectly control your series active filter. So, the error between the sense load voltage and the reference load voltage are used to in the PWM controller to generate the gating pulses for voltage source converter of series active power filter, and this is typically the control algorithm for elimination of harmonic current in voltage fed kind of the load which we were talking about. So, here we have a typically DC link voltage and we have a feedback DC link voltage after the filtering, and we use PI controller for regulating the typically the DC link voltage, so that your voltage source converter can work properly with the PWM control. And we have a load current here, we sense the load current, convert into from voltage PLL, we take cos theta sin theta, and we convert into DQ component which have AC and DC component, and we convert this after low pass filter it comes DC component. So, one loss component we add with that, another is with the voltage control, and we have a reference voltage of terminal voltage and we have a low terminal voltage amplitude, and we put a PI controller. So, this gives us another component, these two add. So, this become quadrature axis current, this is direct axis current, and 0 sequence current is 0, and taking a PI this cos theta sin theta from PLL of the voltage, we convert this IDIQ current into the your reference current for the supply ISA, ISB, ISC star, and we sense the your typically the source current, and we give the current control for the your voltage source inverter working as a series active filter for eliminating the current harmonics in case of your voltage fed kind of load. So, this can work as a, you can call it indirectly series active filter for current harmonic elimination as well as for eliminating the your voltage harmonics and other voltage based compensation. So, the typically the series active filter is used to inject the voltage in series with the terminal voltage to block the harmonic currents, and the harmonics in the supply current are compensated by controlling the series active filter, and the algorithm inherently provides self supporting DC bus of the series active filter. And 3-phase reference supply current are derived using sense voltage, load voltage, and the DC bus voltage of the voltage source converter as a feedback signal, and load current in the 3 phases are converted into DQ0 frame using Park transformation, and this is typically we can call it like the expression for control algorithm. This is the load current which we are changing, and using a Park transformation we are converting to your ILD, ILQ and 0 sequence current, and a 3-phase PLL is used to synchronize these signals with the PCC and or load voltage, from which we are getting cos theta sin theta from there, and DQ component are then passed through low pass filter to extract the DC component of the ILD and ILQ, and the error between the reference DC bus capacitor voltage and the sense DC bus voltage is used to given a PI controller, and the output of which is considered as a loss component I loss of the current and is added with the DC component ILD. And this is the PI controller output, PI controller equation for DC link voltage. This is the reference DC link voltage, this is your DC link voltage controller after the low pass filter, and this is the input for PI controller, and this is the PI controller output, and this is the previous PI controller output and at minus sampling. The digital, this is the digital form of the PI controller like. And now coming to the amplitude of load voltage, we already measuring the line voltage, 2 line voltage, and from we get the 3-phase load voltage, and from which we are calculating this amplitude by using this expression, this amplitude of load voltage. Another PI controller is used to regulate the amplitude of load voltage, and the amplitude of the load terminal voltage is employed over the reference amplitude, and the output of PI controller added with the DC component of ILQ, and this is your load terminal voltage amplitude, this is your load voltage amplitude, and this is the error which is going to this PI controller. Typically this is the output of PI controller output, and this is the your previous output of the PI controller after the saturation and limiting lag. So, direct axis and quadrature axis current component of the reference grid current are here now ISD star equal to IDDC from load part from PI controller output, and ISQ is from again the load part, and this is the PI controller output, and the 0 sequence will be 0 in that case. And now the 3-phase reference grid current in ABC reference frame are typically taken from DQ0 to transformation to reverse Park transformation with the help of this to get the reference grid current ISA star, ISB star, ISC star, and that is typically you can call it the control of series active filter for eliminating the harmonics in voltage effect kind of the load. So, coming to control algorithm for unity vector based unit vector generation for elimination of current harmonic. So, we are sensing the voltage, and from PLL we are getting cos theta sin theta, and this is for DC link voltage. We have a reference DC link voltage, and we are having a sense DC link voltage. With the low pass filter we get the DC part of it, and then pass on to PI controller, and this gives us loss component which we consider the output like of it, and from this voltage from using this we are able to get template here in phase with the your source voltage. We multiplied this PI controller output, and this we consider the reference current, and we take a sense reference source current, and we have a getting signal for series active filter. So, this is the one of the simplest control algorithm you can think about for series active filter for eliminating the current harmonics in voltage fed kind of load. So, a simple control algorithm of series active filter for current harmonics elimination with self supporting DC bus, and the series active filter is controlled such that it injects a set of voltage which cancel out the distortion present in the supply current ISA, ISB, IST, and making them perfectly balanced and sinusoidal with desired amplitude. And since PCC voltage are unbalanced and or distorted, a phase lock loop is used to get the synchronized with the PCC voltage, and 3-phase distorted unbalanced PCC voltage are sent and given to PLL, which generate the 2 quadrature unit vector sin theta cosine theta, and the in phase sin cosine output from PLL are used to compute PCC. In phase 120 degree displays 3-phase unit vector UIUVC use C in phase with the your typically the voltage, and this is typically how we are getting from sin theta cosine theta 3-phase template from this relation. And reference supply current are generated by controlling the DC link voltage of VSC, and DC link voltage is sensed and compared with the reference DC link voltage after filtering by low pass filter getting a DC component, and the voltage error is passed through PI controller to generate the peak value of reference supply current, and this is the PI controller output to regulate the DC link voltage VDC star minus your feedback from DC link voltage after the low pass filter, only DC part, and this is the PI control equation to consider the amplitude of supply current, and the peak value is multiplied with the unit vector to generate the reference supply or load current. So, this is the template multiplied the peak, and this we get the reference, you can call it the supply current, and switching signal for IGBT of voltage source converter are generated by pendulum current controller, which takes as sense supply current and the reference supply current as input or so. So, coming to like now modeling, simulation and performance of series active power filter. This is the circuit of 3-phase 3-wire series active filter, and we have a load here. So, a linear load model as 25 kilowatt 0.8 lagging power factor star connected real and reactive load, and you can say supply voltage are distorted. I mean, we are just putting a band supply voltage for performance of series active filter voltage harmonic elimination and waveform after compensation. So, this is the distorted voltage of the supply, but the load voltage are sinusoidal, load current also sinusoidal because a linear load, and this is your typically the same source current load current because series, and this is the injected voltage by series active filter. So, that the load voltage are sinusoidal, and this is the DC link voltage regulator. So, this is basically voltage harmonic elimination case study, and however, if you see the voltage harmonic distortion, I mean by this is harmonic spectrum 19.970 TAD of this voltage, but the load voltage TAD is reduced to 0.58% only like. So, this is how this work as eliminating the voltage harmonics in in case of linear load like. That is the first function. Another function is series active power filter for elimination of current harmonics, and you can see here 3-phase series active filter is an injection transformer, and we have a I was mentioning that it can eliminate the harmonic currents of the voltage fed kind of load. So, this is our diode rectifier with the capacitive filter is a voltage fed load, and here we have another parallel load, maybe you can call it inverter fed 3-phase induction motor or any even brushless DC motor or any PMSM after this inverter is there like. So, well, with the help of series, the series active filter will be injecting voltage in a manner that we are forcing to conduct all the 3 phases. So, when we have a conduction of all the 3 phases, we forcefully inject the voltage in a manner, I mean how the supply voltage is sine wave, but here we force when all 3 phase diode conducts. So, you will get a voltage here kind of a stepped kind of waveform, which you get a typically 180 degree mode of operation of 3 phase voltage source inverter. I mean same kind of waveform will appear here, because the same this DC link voltage will be reflected here when all 3 phase diodes are conducting, means all the time like typically 180 degree, I mean for positive cycle, 180 degree for negative cycle, and current only then it can be phased with your supply voltage. So, in this case it can provide you, or you can call it by injecting a suitable voltage, it can eliminate the harmonics current. So, you are virtually by injecting this voltage you are blocking all the harmonics which were flowing uncontrolled in this your nonlinear load. So, that is it means series active filter have been more versatile compared to your shunt active filter, and here rating is also less of series active filter like because you have to inject less voltage in that case like. So, coming to after making a modeling and then control of it, you can see these are the 3 phase voltage sinusoidal supply, but the voltage at the input of diode rectifier, which is not going to affect the performance of diode rectifier. Virtually it will improve the performance of diode rectifier, because now the diode is now this capacitor, now this capacitor is charged by 3 phase sinusoidal current. So, you will not find any ripple on this DC link capacitor, because we are now charging forcefully sinusoidal current, and some of the sinusoidal current will be kind of 0. So, then you will not find even the 6th harmonics across the capacitor which is across the load like. So, now you will find this kind of input voltage per phase voltage at the input of your diode rectifier, and with this you will find the supply current are sinusoidal and phase with the supply voltage. So, it means you are eliminating the current harmonics which were very severe current harmonics in this case without compensation, and of course, same is the load current, and this is the injected voltage which we are injecting. This injected voltage is responsible to block all the harmonics current flowing into this nonlinear voltage fed kind of nonlinear load and DC link voltage regulator. So, this is very versatile, and you can understand the rating is this is quite low, because this voltage is not, if you look into this voltage, is current rating will be the same as the load rating, but this voltage you will find is only a fraction of voltage, like even it is not touching even 200, where the supply voltage was already going to be quite high, like also. So, injected voltage is quite low, which we will discuss even numerical problems also later. Earlier also we discussed it was coming only 75 volt. So it was coming almost like a typically 1/3 volt, 1/3 voltage or something, 1/4 volt, 25-30% voltage only, compared to the your shunt filter, like. And you can see without compensation, what was the load current? This was the load current, which have a 61.49% TAD without compensation, without putting series active filter, and which is reduced to now 2.89 the sine wave current. So, this is a major interesting part, because the voltage fight kind of load normally draw the large harmonic current, compared to the current source. Current source, if you take a 3-phase thyristor bridge, the TAD is hardly typically about 30% or less than 30%, 25 to 30%, but in voltage fed load you have a TAD order of 60 to like around 60 to 65%. Now, 60 to 65% series active filter is able to reduce 2.89%, there it is only 25 to 2.85%. So, it is more effective for this kind of the load, and the rating also will be here less, because the rating will be reduced here. You will just see here the current rating will not be more than that, but you have to inject the very less voltage, in this case. So, current rating, if you take a like a shunt filter here, the current rating will be correspond to this, because you have to make this as a sine wave, but the voltage rating is the full. So, rating of the shunt active filter for such kind of compensation of your let us say for voltage fed kind of load, rating will be very high, but the series active filter rating will be much smaller, like also. So, that is very interesting observation with the series active filter. And sometime what we do, DC link of the load, we can connect with the DC link of your series active filter. So, that give interesting that you save one capacitor, and now you do not need to have a self supporting DC bus from the control, because this voltage is already at the output. You want to control, that is also you can control even higher also, or you can regulate the voltage across the load also with the help of this, because this control can provide. So, you can regulate this voltage also across the load, which certainly will be regulating the active filter. This we call it like a, people call it like a sometime active rectifier with the simple diode rectifier for the compensation. So, this was very interesting. Study have been reported in the, even industry have adopted such kind of concept, like. So, series active filter for elimination of current harmonic with common DC bus of the load with series active filter. And you will find the performance here, that you have a supply voltage, again you have a input of diode, this is the voltage we are talking about here, and the current in the supply sinusoidal, load current is also sinusoidal, and you can see the injected voltage is quite low. This is the injected voltage, which is the difference of these two voltage. So, if we bring this, it means we are forcing the all the 3 phase diodes to become sinusoidal, and certainly the DC link voltage you will not have even, you will not find any, virtually you can call it the ripple in the DC link voltage, like also. So, that is the another advantage, that you know to have even the regulation of DC link voltage if you do not want, it only you have to properly design that DC link voltage is enough to operate this series active filter, or if you want to regulate, you can regulate that also. So, that is the typically is working with the series active filter for eliminating the current harmonics in voltage fed kind of load. And you can see without again the compensation, if you do not have a series active filter, this was the TAD, and now it is TAD reduced even 1.13%. So, current becomes almost sinusoidal in such kind of voltage fed load, and the rating is also quite low in this case, like but you are not to inject the voltage quite large. Just see the how much voltage you are injecting in series with. So, it is much lower, current is the same as the load current, and that peaky current is also reduced, like you can see. Here this was the current, it was like a touching even more than, it was coming more than 50 or so, but here it is not touching more than 50, and that is a virtually a sine wave. Here crest factor you will find quite high, like also. Should we stop here, like?